Hello. In the last classes, we have studied about covalent bond and ionic bond. In this video, we will study about metallic bonds. It is a type of bond which holds the metal atoms together. As we know, metals have many special properties, like they have very high conductivity, both thermal conductivity and electrical conductivity. They have metallic luster, means they will have a kind of glow. They have properties like malleability and ductility, and also metals have very high tensile strength. But all these properties cannot be explained by simple covalent bond or a simple ionic bond. To explain all these properties, we have a type of bond called metallic bond. As we know, the metal atoms are arranged closely together in a metal lattice. The atoms are held together or closely packed in a metal lattice. And the forces which holds, the attractive forces which holds together the atoms of a metal in its metal lattice is called a metallic bond. So a metallic bond is simply the attractive forces which holds together the atoms of a metal in a crystal lattice. There are different models or theories which explain metallic bonds. Three of them are listed here. The first one is called free electron theory, which is also called electron C model. The second one is called valence bond model, and the third is called band model. This band model is a molecular orbital approach to explain the metallic bonds. We will see about the free electron theory, which is also called electron C model of metallic bonding. As we know, when an atom loses an electron, it becomes a positively charged species, which we call as a cation. Now, according to the free electron theory, when a metal atom loses an electron, it becomes a positively charged species, and this positively charged species is called a kernel. In other words, when a metal atom loses an electron, the part of the metal atom that is left behind, we know that is positively charged, and that part is called a kernel. We'll take lithium as an example to understand this. The electronic configuration of lithium is 1s2, 2s1, and when one electron is lost from this lithium, it becomes lithium plus ion, and this lithium plus is what we call as a kernel, and its electronic configuration will be 1s2. So in this lithium metal lattice, the kernel will be Li plus. According to this model, as you can see in the figure, the kernels occupy the closely packed fixed positions, and the electrons occupy positions in between the kernels. So it will look something like a sea of electrons in which the positively charged kernels are spread. That is why it is called electron sea. And the metals will behave as if it is an assemblage of kernels immersed in a sea of electrons. And according to this theory, the kernels will remain stationary. These green dots represent the kernels and the red ones represent the electrons. These kernels will remain stationary, whereas the electrons are mobile. Means the electrons can move about freely inside this metal lattice, but the kernels cannot move. Now, one kernel is not associated with an electron, means since the electrons are freely moving about, each electron will be under the influence of a number of kernels. Similarly, each kernel will belong to a number of electrons. So, the kernels and electrons are attracted to each other, and this force of attraction between the kernels and the mobile electrons is is called a metallic bond. It is this force of attraction which holds together the metal atoms in its metal lattice. So we will define metallic bond according to free electron theory as follows. That is, the simultaneous force of attraction between the kernels and the mobile electrons which hold the metal atoms together is called a metallic bond. Now, as you can understand, the strength of this metallic bond will depend on two factors, that is valence electrons and also the nuclear charge of the metal. And the strength of metallic bond is directly proportional to both these factors, that is the number of valence electrons and also the nuclear charge of the metal. This electron-free C model or the free electron theory is also known by another name, that is electron gas model. This is because, as we know, there are a number of mobile electrons inside the metal lattice according to free electron theory, and these electrons are completely free to move about inside the metal lattice. So its behavior can be compared to the behavior of gas molecules. So that is why it is called electron gas model. Now this free electron theory can explain almost all the properties of a metal. Now we are going to see the different properties of metal and how this free electron theory can explain these properties. First, let's take the property of electrical conductivity of metals. We know metals are highly conducting in nature, and if this is a metal piece of metal, if we connect that to an external potential, we can see the metals will conduct electricity. And according to free electron theory, this property of metals is due to mobile electrons. That means the electrical conductivity of metals is due to the presence of the mobile electrons in the metal lattice. When a potential is applied to this metal piece, as we know, since electrons are negatively charged species, they will be attracted to the positive terminal of the battery, and the electrons that are removed in such a manner will be replaced by new electrons from this negative terminal. So this will result in a continuous flow of electrons, and this continuous flow of electrons is what we call as electricity. So that is why metals conduct electricity. If you connect this metallic rope to a battery, that is if you apply a potential, instantaneously thermal conductivity will occur, or the metal will start conducting electricity. But in the case of thermal conductivity, if you heat one part of the metal, it will take some time for the other part of the metallic rod also to get heated up. So I say thermal conductivity takes time, whereas electrical conductivity is instantaneous. The third major property of metals is that they have a metallic luster. Metallic luster means, as you know, the metals have a shiny appearance, and this is also due to the presence of mobile electrons according to free electron theory. We know that light is an electromagnetic wave, and this electromagnetic wave has both electric field and magnetic field associated with it. So when a light falls upon a metal, the electric field of this electromagnetic radiation, that is light, sets the electrons on the metal surface into vibrations, or I can say to and fro oscillations. We have also studied that a moving charged particle will emit electromagnetic radiations. In this case, electrons are negatively charged species, means they are charged species, and therefore if they are moving or oscillating, they can also produce electromagnetic radiations. And this electromagnetic radiations will be emitted in the form of light. So what happened here is that light first fell on the metal. The electric field of the light and interacted with the electrons on the metal lattice, setting the electrons of the metal lattice into to and fro oscillations. And these charged electrons, while oscillating, will emit electromagnetic radiation in the form of light. So in short, when light falls on the metal, it appears that the light is being reflected back, and therefore the surface will appear bright. Actually, it is not the light that is falling on the metal that is emitted back or reflected back. There is some other process going on here. When light first falls on the metal, the electric field of the light will interact with the electrons of the metal lattice, so that the electrons of the metal will undergo to and fro oscillations. And since the electrons are charged species, these oscillating electrons will emit light. Okay, but what appears to us is that light is falling on the metal and it is getting reflected back. Actually, that is not happening. When light falls on the metal, what happens is that this kind of interaction will occur. But what we feel is that when light falls on the metal, it is getting reflected back, and we'll see that there is a shiny appearance. So this is how free electron theory explains the metallic luster. The fourth important property of metals is that they are highly malleable and they are highly ductile. Both these properties can be explained using free electron theory. And according to free electron theory, these properties occur due to the non-directional nature of metallic bond. Means the metallic bond do not have a direction. It is spread in all directions. Suppose this is a metallic lattice or a piece or a metal block. This metal block has positively charged kernels and also negatively charged electrons, right? So suppose you are applying a stress here, means you are striking this metal piece with a hammer or something on one part of the on this part. That means the metal is undergoing some kind of stress. So when this kind of stress is applied, the kernels can easily be moved from one lattice side to another, as you can see in the figure. When you apply a force here using a hammer, the kernels will slide across to another part. So this is what makes the metals highly malleable and also highly ductile. The crystal structure does not change, but the shape will change. Then, as we know, metals also have high hardness and high rigidity. They are very hard and rigid. And both these properties can also be explained using free electron theory. The hardness is proportional to the strength of the metallic bond. Greater the strength of metal, greater will be the hardness of the metal. And the strength in turn is proportional to the number of valence electrons, but inversely proportional to the size of the kernel. As the size of the kernel increases, the strength of the metallic bond decreases. Also, if the number of valence electrons increases, the strength of metallic bond also increases. If you take the example of alkali metals like lithium, potassium, etc., we know they are metals, but they are very soft metals because we can even cut them with a simple knife. This is because alkali metals have large kernel size, and when the kernel size increases, we have already seen that the strength of the metallic bond will decrease. Also, there is only one valence electrons in the case of alkali metals. We have already seen the example of lithium. When one electron is lost, lithium becomes Li plus kernel. There is only one valence electron, so only one electron can be lost. So the number of valence electrons is lesser, and therefore the strength will also be lesser. So alkali metals form only weak metallic bonds, and that is why they are very soft. They can be even cut with a knife. The next property is tensile strength. Tensile strength is a property of metals to stretch without breaking. If you have a metal rod and if you stretch it by catching on both sides, by holding on both sides of the metallic rod. It will stretch without breaking. Of course, we cannot do it with our hands. There should be some kind of a device to do that, a machine to do that. If you stretch like that, the metal will resist breaking. It will just simply stretch. This property is what we call as tensile strength. And this tensile strength is due to the strong electrostatic force of attraction between the kernel and the electrons, because we know kernels are positively charged species and electrons are negatively charged species. So there is a force of attraction or electrostatic force of attraction between these kernels and the electrons, and that is why the metals can stretch without breaking. So this is how free electron theory explains the different properties of metals. But even though this free electron theory can explain many properties of metals, limitations for this free electron theory, because the model cannot explain the variations in properties of metals, because all metals do not behave equally. We will give you some examples. Say uh, the melting point of mercury is minus 39 degrees Celsius, that is very low. As we know, at room temperature, mercury will be existing as a liquid. But tungsten is also a metal which melts at a very high temperature, that is 3300 degrees Celsius. So this kind of variation in the melting point of metals cannot be explained using free electron theory. Why some metals have a low melting point? Why some metals have very high melting point? This cannot be explained using free electron theory. Also, if you look at the conductivity of various metals, different metals have different conductivity values. Say for example, if you take copper and bismuth, both are conducting, but the electrical conductivity of copper is almost 50 times than that of bismuth. So why this kind of variation occurs in electrical conductivity of metals? This cannot be explained using free electron theory. Also, we know that some metals are colored. Say for example, gold is golden yellow in color, copper is brown in color. But there are various other metals also which do not have any kind of color. So why this kind of variation occurs cannot be explained using free electron theory. Also, another thing is that certain metals like sodium and potassium are very soft. We have already seen that. When we cut that, we can even cut these metals with a knife. Whereas various other metals, say for example osmium, is very hard. It is so hard that it can scratch even glass. So why this kind of variation occurs in the properties of metals? This is a dilemma for free electron theory. Free electron theory cannot explain such variations in properties of metals. So that's all about free electron theory. Now let's see the valence bond model of metallic bond. Let's take the example of lithium. It is understood that in the crystal lattice of lithium, each lithium is surrounded by 8 other lithium atoms. If you take this lithium, you can see it is surrounded by 8 other lithium atoms. If you take this one, the neighbors are 1, 2, 3, 4, 5, 6, 7 and 8. So there are 8 immediate neighbors for one lithium atom, and also there are 6 other next to nearest lithium atom. Means if you consider this one, this lithium is the nearest neighbor, and then you have next to nearest neighbors. This is the next to nearest neighbor. So for each lithium atom, there are 8 nearest neighbors and 6 other next to nearest lithium atoms. We know that the configuration of lithium is 1s to 2s1, and there is only one valence electrons in the case of lithium. So if you consider that a lithium atom forms a bond, a covalent bond, because there is only one electron, it can share this one electron only with another lithium atom, which means lithium can form only one covalent bond with one neighbor. Like this. One lithium can form only one bond with the nearest neighbor. But according to this valence bond model, the lithium-lithium covalent bond is assumed to resonate between all the 8 nearest neighboring atoms, and also to some extent to the next 6 next to nearest neighbors. So we can show the resonance like this. The bond between these two lithium atoms is now shifted to these two lithium atoms, as you can show in the second resonating structure. So this type of resonance stabilizes the metallic bond. This is how the valence bond model explains metallic bond in metal atoms. Now we can also consider the formation of Li minus ions and Li plus ions, which can also enter into resonance. Now how is this Li minus and Li plus formed? The configuration of lithium is 1s2 Then we have 3 vacant p orbitals also present in lithium. And we know the 2s orbital and 2p orbital have almost similar energies. The energy difference between 2s and 2p orbitals is not greater. No, there is not much difference between them. Therefore, the 2s electron of one lithium atom can be transferred to the 2p orbital of another lithium atom. Okay, the 2s electron of this lithium atom can be donated to the 2p orbital of another lithium atom. So this will lead to the formation of Li plus ions and Li minus ions. The lithium atom which donated this electron will become Li plus, and the other lithium atom which has accepted this electron will become Li minus ion. So in this way, Li minus ions and Li plus ions are also formed. Now let's consider 4 lithium atoms. To distinguish between these lithium atoms, we are calling it as Lia, Lib, Lic and Lid atoms. Suppose the lithium D atom transfers an electron to Lib atom. We know the configuration is 1s2 Now if Lid donates one of these electrons, that is a 2s electron, to Lib, the Lid will become Lid plus and this electronic configuration will be 1s2. Lib will now become Lib minus because it has now one electron greater. The electron donated from Lid is occupied now in the 2p orbital. So now you can see we have Lid plus ion and Lib minus ions. Now in this Lib minus ions, there are electrons in the s orbital and also one of the p orbitals. Now this 2s orbital and 2p orbital will hybridize to give 2 sp hybrid orbitals. And these 2 sp hybrid orbitals will now overlap with the other 2 lithium atoms. That is the 2 sp hybridized orbitals. One of these sp hybridized orbital will overlap with the half-filled 2s orbital of Lia atom. The other sp hybrid orbital will overlap with the 2s orbital of Lic atom. So in short, all these 4 lithium atoms will be bonded to each other. So this is how the valence theory explains metallic bond. And the different resonating forms can be written like this. you can have a number of resonating forms like this. Here you can see there is a covalent bond between two lithium atoms, and there are many such lithium atoms in this metal lattice. Now this bond can resonate like this, means the bond between this can be shifted to bond between the first lithium and the second lithium, which lies on the bottom. So that is a second resonating structure. Then you can also consider the formation of Li plus ions and Li minus ions, as we have mentioned earlier. So all these can also enter into different resonating forms. So this is the valence bond theory. Now let's see the third theory which explains metallic bonding, that is a band model, which is based on the molecular orbital approach. We know that each metal lattice consists of a large number of atoms, and each of these metal atoms will have a number of atomic orbitals also. The atomic orbitals of the metal atoms with same energy and same symmetry will overlap to form molecular orbitals. And these molecular orbitals are very close in energy that they form bands of energy levels. Means, since large number of atomic orbitals combine, forming large number of molecular orbitals with same or almost similar energies, they form bands of energy levels. Each energy level in this band is capable of holding 2 electrons. Now, depending upon the type of orbitals which overlap, different bands are formed. Say for example, 1s orbitals overlap to form 1s band, 2s orbitals of all the atoms in the metal lattice overlap to form 2s band, and so on. The arrangement of electrons in different bands determines the characteristics of a metal. What we call as a valence band, and the high energy band is called as a band. That is, the highest occupied band is a valence band, and the lowest unoccupied band is a conduction band. So if you can see, this represents a valence band and this red one represents a conduction band. And the energy difference between this valence band and conduction band is what we call as energy gap. It is also called forbidden zone. So forbidden zone or energy gap is the energy gap between the top of the valence band and the bottom of the conduction band. And this energy gap determines whether a metal is a conductor, an insulator, or a semiconductor. If say for example, in the case of insulators, the electrons in the valence band and the conduction band are separated by a very large energy gap or forbidden zone. So if you try to excite an electron from this valence band to the conduction band, it becomes impossible because of this large energy difference. So such atoms or such molecules are considered as insulators. In semiconductors like silicon, germanium, etc., the energy gap between the valence band and conduction band is very small. So thermal excitation of electrons can take place from valence band to conduction band, and therefore such materials will be conducting. Now this conduction or the conductivity can be increased by adding a doping material, which can increase the conductivity because of this very small energy gap. We are familiar with that. Another method to increase the conductivity is to increase the temperature. As the temperature increases, conductivity of semiconductors also increases because the electrons in the valence band get thermal energy to be excited to the conduction band. Thus, the electrical conductivity of semiconductors increases with increasing temperature. But when we move on to metals, The energy gap between the valence band and conduction band is zero. In fact, the valence band and conduction band may overlap with each other. Therefore, it will be very easy to excite an electron from this valence band to conduction band, and therefore the metals are highly conducting in nature. So this is a band model which explains the metallic bonds, and band model can also explain the existence of different types of materials like insulator, semiconductor and metals.